Okay, this tutorial is on initial value problems, particularly the initial value problems y prime is equal to lambda y. Slope y prime is equal to some constant lambda multiplied by the value of y on the x-axis here and against time on the x-axis against y on the y-axis. And the point is that the slope is equal to some constant by the actual value of the function. We need an initial value to start off with, y0. And the slope of that function at that point is y0. So as well as being equal to y0, it is y0. And then, so the slope comes off here at y0, and as it gets higher, if that's positive, it gets bigger, y gets bigger, and the slope gets higher. The slope is constantly increasing, so you have an exponential increase in the value of the function with time. And that's the nature of that function there. So we can also express that as y prime as f of t and y is equal to lambda y. So the y prime is some function of both time and y. It's equal to lambda y. So in order to set this up, we need to create our initial value. y0 is equal to, I'm going to put that in this cell here and give it a name. Set equal to 1 for want of a better value. Call that y0. And it should be y0. And we need our constant lambda, so I go insert symbol. I've used it before, so it's there. Search through it to get it. So lambda equals, why not call that 1 as well? Then we also need, we're doing a numerical solution, so we need to break up the time into time steps, to blocks of time. I'm going to use a uniform time step, which we call h equals, and that'll probably need to be a bit smaller to maintain stability, so put that equal to 0.5. Call this cell B2, call it lambda, and call this h. So they all have names, so I can try them with the shorthand to use them in formulas. So first of all, I'm going to put in some values of time. So t is equal to 0. And every subsequent cell, just put it the previous one plus h. So it increments it by h each time. Do from 0 to 3. And first I'm going to put in my exact solution. This is a solution to the actual equation. It's not a numerical method. It's not in any ways approximate. It's the exact solution. And the exact solution is that y is equal to y0 by e to the power of lambda by t. So we put this as equal to y0 multiplied by e. Function for that is exp. E to the power of lambda multiplied by the value of time, which is in this column here. Close the brackets. You have that. You only have to do that once. You fill it down, and it will repeat it for the other values of time. So as time increases, so does it. Right. So next, I'm going to try an approximation to that now, a numerical method called the forward Euler method, or more commonly just referred to as the Euler method. Okay, so the numerical methods, they work by using a simplified form of the solution over the time step. And generally, the smaller the time step, the more accurate they are. So we start off from a known point, and we know that the initial value is y0. We start from there, and then we take, so the slope at the initial point is equal to slope y prime is equal to lambda y. The slope will be equal to lambda by, and this is the only value of y we have, 0. That's the slope, the rate at which it's changing. The amount by which it changes, if we take the slope multiplied by the time over which it's changing, we have the amount that it changes over that time. And then, so that's the amount that it changes over one time step. We add that to the original value. We have its value after one time step. So if we select this, just C6, add the incremental change h lambda by y0, h lambda by y. Will give us an estimate of the value of y of 1.5 compared to 1.65 for 648 here. So there's a certain level of error there. But we have it put in a formula so that we can fill that down, and we see that get increments the values. You can see that these significantly undershoot the value of the analytical. By the time 3 seconds is 11.4 compared to 20.08. So there's a significant difference. An alternative possibly is it's known as the backward Euler method. So once again, it's a numerical method. We start from a known starting point, y0. All right, y0. And expression for the next solution. So if we call this yk, this is yk plus 1. So yk plus 1 is equal to the previous value, yk, divided by 1 minus h times lambda. What it works out as. So it gives us a value of 2 for the first. And we'll try filling that down. We can see that this backward Euler then significantly overshoots the value. So while the forward Euler undershoots, the backward Euler overshoots. Maybe there's another method called the trapezoid method, which is simply the average of the forward and backward Euler. So I'm going to put that in here. And all we have to do is, we've already calculated the forward and backward Euler, so we just put in y here is equal to the average of the forward and backward Euler. And fill that. Now I'm going to try comparing these by plotting them against each other. So I select all of these now, go to Insert, I select Scatter Chart there, and select the Scatter Chart with the symbol showing the actual points of the calculations. And plot it out there. Let's try and enlarge this slightly. Is that big? So we can say our analytical solution is the blue line there. The Euler method undershoots it. The backward Euler significantly overshoots it. Because of the inaccuracy in the forward Euler, or the backward Euler. So the trapezoid is fairly inaccurate as well. So none of these are really satisfactory for this particular problem now. So I'm going to try using another method known as it's a subset of the Runge-Kutta methods known as Hune's method. And in order to do that, you make estimates, two estimates of the slope of the function in the time step. So we call those slopes K1 and K2. And based on them, we take an average of those two slopes in to give us the value for y using Hune's method, which we'll put here. So the first estimate of the slope, well, we start with our initial value of y0 equals y0. Based on y0, we're going to calculate first slope. So the slope y prime is always equal to lambda y, so we'll just put that equal to lambda by the only value of y that we have, which is from the previous calculation. For K2, we come up with an improved value of y by incorporating this slope that we've just calculated here. So this equals, so slope is equal to lambda y, so it's going to be equal to lambda multiplied by this value of y plus slope K1 by the time step h. Slope by time step gives you the incremental change. Add that to y0. We have an improved value of y. Multiply that by lambda y to give us the slope. Oh, we get an improved value of our slope there. Then we take the average of this and use that as our average of this and of this. So that's our slope. Multiply the slope by the time step to give us the incremental change. Then we add that to our previous value of y. We have hx plus h by the average of k1 and k2. So that gives us 1.625. Compare that to 1.65. So that gives us much better accuracy than any of these methods here. So that involved 3 calculations, but now when we iterate that, computer does it all. So we get, after 3 seconds, again 18.4 compared to 20.8. So it's much more accurate than any of the others. Let's try incorporating Hewn now into our graph. So we right-click on any of the graphs, select data, and add. Our series name is Hewn. Edit that. And our x values go back to, that's time. I'm on the x-axis. And our y values. Select the Hewn column. And okay that. Just save that. Okay, so that's our analytic, that's our exact solution. This is the Hewn method here, so you can see it's quantum leap in the level of accuracy for the compared to the others. See, there is still some discrepancy since we're getting larger as the calculation proceeds. So we have the option of using the fourth order Runge-Kutta, the full Runge-Kutta method. So usually when people in the business say Runge-Kutta method, they mean the fourth order Runge-Kutta. Hew's is a bit simpler and shorter, but we'll see what using the fourth order Runge-Kutta can do for us in terms of accuracy. This down here. So the fourth order Runge-Kutta over here in the corner shows you need to calculate 4 estimates of the slope. Then you take a weighted average of them, k1 plus twice k2 plus twice k3 plus k4. So let's add up those coefficients as 6. So we divide that by 6 to give us the weighted average. And it's weighted towards k2 and k3, which are generally more accurate. And multiply that by h, and multiply the slope by h, and add that to the previous value of y, yk, plus yk plus 1, the next value. So let's call these columns k1 to k4, k2, k3, and k4. And all this, so that's where I'm going to put y is calculated by the Runge-Kutta method. Runge-Kutta. So k1 is equal to value of the function at tk and yk at the previous values of t and y. We have our first solution equals y0. So we're going to use that y0 as yk here. k1 is, so the function is lambda y, so equals our slope, lambda times y. That's the only value of y we have, so and we put it in there. So our initial guess of the slope is slope of 1. So the second one, k2, is equal to, we're evaluating the function lambda y at t plus h over 2. And so halfway through the time step. And our value of y is y plus k1 by h over 2. So we use an improved value of y to calculate lambda y. So lambda times that previous value of y plus slope we just calculated, k1 by h over 2. And so we proceed then to sort of do the same thing again, but now we used, instead of using K1 in this expression, we use K2. We'll try filling it across and see what I get. Okay, we're not quite there yet because we need instead of N6, we need M6, new Y0. So this is M6 plus K2 by H over 2. And then multiply that by lambda to give us our slope, lambda y. And the K4 then, so function f evaluated t plus h. So at the end of the time step, that's y plus h by K3. So is equal to so yk, previous value of y, plus h by K3, slope K3. So that's 4 estimates of the slope there. And so we take the weighted average of them. So yk plus 1 is equal to yk. Yk is the previous value of y on the previous calculation, so our starting point, plus h multiplied by this weighted average, k1 plus 2k2 plus 2k3 plus k4. And we divide that by 6. It gives us 1.648 compared to 1.648 there. So give us a much better level of accuracy now compared to any of the previous methods. And so now I take that, I can fill that down. And after 6 time steps, I'm going to get 20.064 compared to the exact solution, 20.085. So I'm expecting a huge improvement in the accuracy here. So again, right click on any of the graph, select data. This is our Runge-Kutta method. And sorry, click add first. And call it Runge-Kutta. My x values, which are here. And delete this and select your y values. And okay that. Okay. So apparently this green line, which previously the analytical, is now Runge-Kutta. We can't distinguish between them. Maybe if I try it. So by increasing the time step, it makes the calculation more difficult for each of the methods, and will exaggerate the error. Increase the time step there. And here the Runge-Kutta. Here we have the analytical. Backward Euler, it's gone unstable. So it's not calculating anything really. Or neither, the trapezoid is derived from that, so it's gone unstable as well. And so you can see that we're having still very accurate for the Runge-Kutta method. Barely any error. That's a tiny error there. The Hume's method showing some level of inaccuracy. Forward Euler is way off. Let's say the backward Euler and trapezoid method have gone unstable at this stage. So we see that using higher order Runge-Kutta gives us excellent accuracy, even at very large time steps. So it's a quantum leap in accuracy over any of the other methods. increased level of calculation involved, but you only have to do that. You only have to input that once, and once it repeats the calculation and iterates, you get a great improvement in accuracy.